So today I'm going to speak about retrieval augmented generation, basically try to give an overview of what's happening recently in this field, especially like a review of the recent approaches. I'm currently working with Eugene. I'm a PhD researcher with him. And before that, I was working in a conversational AI company called Amelia. And now Amelia and IPsoft are two companies, but essentially they were one company and working into conversational AI. And before that, I did my engineering from BITS Pilani, India. If you have any questions, please interrupt me in the middle, and I'm happy to answer your questions because I think there are lots of keywords which I've assumed like some of them the audience will know, like especially LLMs and what's training, testing, and what are hallucinations. But I'll try to cover as much as depth as possible. But like in general, feel free to pause me. We've seen like recently there is lots of large language models, especially ChatGPT, Gemini, and many others have shown impressive strides in numerous benchmarks. And we see them ourselves as well, showing like radically great performances in math benchmarks, reasoning benchmarks, open domain QA benchmarks. But all of this is hinged on like the model being in a vanilla architecture fashion. That is, you provide a user query to it, and the model will then generate a response. And the model will be basically trained for a few months, and that the training process would be done on a static data set. So there are lots of problems in this particular vanilla architecture. One is that the training data is generally outdated by the time they are deployed, since LLM's training process could extend to even up to a few months. And the vanilla LLMs might be unfamiliar with domain-specific information, something which, let's say, if we ask ChatGPT something very specific about the library of Emory, something like that. Besides, LLMs might be inaccurate in recalling relevant information. And besides, once a model has been trained, it can be hard to modify or delete information from the model. So an important consequence of such vanilla architecture is basically the propensity to generate hallucinations. So for example, on the right, an older version of earlier version of ChatGPT is prompted, what is the world record for crossing the English Channel entirely on foot? And the model provides an answer which is fluent, coherent, and convincing enough to deceive readers, as if it's really possible to walk the distance on foot. So there are lots of different hallucinations which are possible like these. And in general, in the literature, like there is one, hallucinations are classified into like three general types. So for example, on the question on the right, can you recommend a delicious recipe for dinner? The LLM response generally we have seen like LLM responses show three different types of hallucinations. One is input conflicting hallucination, in which what the LLM responds conflicts to something what the LLM has been asked for. Something, so it's saying lunch when the question is regarding dinner. Then there could be context conflicting hallucinations, in which the LLM response might be contradictory to something mentioned earlier in the context. So this could be in a large conversational setting in which there are to and fro conversations between the user and the LLM, and the LLM has generated something contradictory. Or there could be fact conflicting hallucinations. That is, the LLM has generated something contradictory to world knowledge or knowledge which is generally authoritative, like something like Wikipedia. So these hallucinations, which are like the biggest, one of the most disadvantages, are an outcome of vanilla LLMs. And one solution to these vanilla LLMs, as well as the hallucinations, is basically retrieval augmented generation, which we'll look at in these set of slides. So retrieval augmented generation basically provides retrieved information, that is external information, at runtime. So retrieval augmented generation then provides an ability to provide additional information which is not a part of the training data of the LLMs. Besides, domain-specific or proprietary data, which are generally not available as a part of the pre-training corpus, can also be available. And even empirically, it has been shown that using retrieval augmentation has been shown to improve factuality of responses. And most importantly, it is highly optimizable. It's highly feasible to optimize the retriever. So an external retriever, which I'll talk about in the next slides, is basically something you can assume like you send a query. It's like a search engine. So you send a query and it generates a set of documents. So at any point of time, so that there's a backend index which generates, which retrieves these documents. So at any point of time, we can, if you want to get rid of any of those documents, we can get rid of those documents. So we can decide to opt out. But that's not possible in a vanilla architecture where the LLM weights have been trained for over a long time. And once that the weights are quite like static in nature. And there's an advantage of better provenance. That is, once the LLMs has generated some response, we can even retrieve external information to attribute it to external sources. So there is the benefit of attribution. So essentially, like we can see in the figure, in the base case, we have a user query, which on the left, we have a user query, which is sent to the model, which generates just a response Y. But in the retrieval augmented case, we'll have a user query, which generates retrieved information and gets documents and then uses that to generate. So in the most basic sense, a basic RAG pipeline consists of at least one generator and one retriever. So, and the generator could be anything like an autoregressive decoder or a sequence-to-sequence transformer, along with a retriever, which can fetch ranked pieces of text, which are relevant to a given query, just like modern search engines. But RAG architectures can get easily complicated, depending on the task of interest, as well as the accuracy of the retriever and the generator. So complex RAG pipelines generally build additional components around these, like query reformulation, neural re-ranking, all of which I'll just give a brief overview of them. So like this figure is a lightweight superset of the different components involved in typical RAG pipelines. And most of the RAG approaches generally have a subset of these components. So in the base vanilla case, we have a user query being sent to the generator without retrieval. Or we could have a retrieval augmented case in which we could have a model which decides whether we should retrieve or not. If we decide we should retrieve, then we could have another model which generates a query, that is reformulates a query. We could have another model basically which makes the query very specific to the set of documents. So there could be another step of reformulation. Then once those documents are generated, and those documents could be generated from, the documents could be retrieved from either a knowledge base like Wikipedia, or the retriever could act as a search engine like Google or Bing. So once the documents are retrieved from any of the indices or a search engine, then we have a ranked set of documents that is shown in the figure, like D1, D2, D3, D4. If the first stage of ranking is not good enough, we might have another model to re-rank those documents and get another set of documents. We further might want to do some refinement that could be like either chunk some pieces out of the document, or maybe summarize those documents, or make them consistent to what the generator has been trained on, and then feed them to the generator. So this is essentially what a RAG pipeline would generally contain, like a subset of these. And this is what is retrieval. This is when retrieval is done before inference. That is when the output of the generator before it's shown to the user. But retrieval augmented generation could also be done post inference. That is, once a model's output has been generated, we could use retrieval to basically find evidence to how good the generation is. So for example, here in this figure, once a model is generated, then we retrieve from an external database to get some evidence documents, and then we use those evidence documents to produce an attribution report. So that attribution report will kind of work like add a level of interpretability to the process. So many design decisions dictate what a typical RAG architecture would look like. The first and foremost, the motivation, like why to retrieve. I think we are pretty clear on this, that basically we retrieve to generate when the generator has lack of knowledge, or to establish the veracity of text. What to retrieve? We could retrieve tokens, we could retrieve entities, we could retrieve passage, or we could even retrieve APIs. Then how to retrieve? Whether we want to use a sparse or a dense retriever, or a combination of both. And I'll explain these in the next slide. And whether you want to use both, or whether you want to use a re-ranker to re-rank them. Then when to retrieve? This is an interesting question. And I think if people are interested in this question, this is a very nice question to even solve, even like in a rule-based setting as well as in a model architecture. I'll discuss these in the next slides. So you could decide to retrieve only at inference. So you could decide to retrieve from this time of fine tuning, or just at inference, or you could decide to retrieve at certain time steps or retrieve always. And where to retrieve from, that is what kind of source. You have a leucine index or a phase index. You could have a sparse index or a dense vector index. And once the retrieved information is obtained, how do we integrate such retrieved information? That is, we could either concatenate the text, concatenate the retrieved information in context, or like use a fusion and decoder kind of architecture.